Hello, I'm Fumiya from Kagawa University. Today, I'd like to talk about microsensor device for minimally invasive measurement of moisture storage in plant shoots. First, I'll tell you about the background. Appropriate irrigation and fertilization based on the three factors are necessary to produce crop efficiently. Recently, there is an active movement to measure these factors and to automate agriculture based on the data. Currently, of the three factors, plant psychological information is estimated from soil condition analysis. However, the result of soil condition and plant condition are different. In addition, soil condition analysis is impossible to measure the end of a plant stem. It is the most important part of a plant. Therefore, realization of a directly measuring for the end of the plant stem is desired. Next, I'll talk about the purpose of our study. Monitoring moisture dynamics is important for proper plant growth management. As shown in this figure, there are three parameters of moisture dynamics: moisture potential, subflow velocity, and moisture content. By measuring each parameter, we can comprehensively understand the moisture dynamics of plants. In previous studies, these three parameters have been evaluated for tree and shapes. However, there is no established method for minimally invasive of moisture content in herbaceous plants such as crops. The subflow velocity sensor has already been realized as shown here. Therefore, the purpose of this study is realization of sensor device for minimally invasive measurement of moisture storage in plant shoots. We propose this novel sensor device. Three sensors are mounted on each probe, and this sensor device is used by inserting it into plants. This enables real-time and direct measurement of a plant's moisture dynamics. Next, I'll explain the moisture content sensor. Plants change their internal moisture content due to transpiration. Therefore, measuring plant moisture content is similar to measuring plant moisture dynamics. This is the moisture content sensor. The measurement method of the sensor takes advantage of the characteristic of the impedance, which varies with the amount of moisture absorbed. However, the moisture content values depend on the EC value. So in this study, the EC sensor must be configured to attain an accurate moisture measurement. Specifically, two probes are used, one with the EC sensor and the other with a resistance temperature detector, RTD. This is a sensor that measures EC value, the AC to electrode method. EC sensor measures EC value and RTD performs temperature compensation. Then I'll explain the moisture content sensor method. Here is the measurement method of the moisture content sensor. This sensor is based on the principle of commercial humidity sensors. The impedance change according to the amount of moisture absorbed by the moisture sensitive membrane of the sensor. This impedance is represented by Z in this formula. The moisture content WC is calculated according to this formula. The sensor consists of two layers of electrode and moisture sensitive membrane. Therefore, these elements are integrated on the silicon wafer. This is the fabrication process. First, an oxide film and AU chrome wiring was formed on a silicon wafer. Next are 10 micrometer thick layers of moisture absorbent polyimide was fabricated onto the electrode. And the needle-shaped sensor is completed after silicon dry etching. This is a photograph image of the fabrication result. Here is a microscopic image of the broth. We are able to confirm that moisture content sensor and RTD EC sensor are mounted on probes. The length of the probe is 1 millimeter, which is set to consider the distance from the tomato skin to the xylem. From here, I'll explain experimental method and result. Generally, plant irrigation is performed on a daily basis. Therefore, the moisture content sensor is required to measure the response time at the minute scale. So we first measure the device response characteristics. Experiments were performed on a cotton fabric pieces with moisture content adjusted to 90% and 50% using an electronic balance. Next, we measured the impedance change over time by covering the moisture content sensor with a cotton fabric and then removing it. This figure shows the relationship between the response time and the impedance value. The blue dot is moisture content 50% and the red dot is the moisture content 90%. The fabricated sensor required about 30 seconds to obtain a response, which is close to the target value. From this result, the sensor responsibility result was better than the time required for plant irrigation. Next, let's talk about calibration experiments. For the basic characteristic experiments, the sensor was evaluated by placing a cut-off tomato stem on the electronic balance. The change in impedance and weight were then measured as the plant dried. In addition, we simultaneously measured the EC value and temperature in the plant by using a fabricated EC sensor and RTD. This figure shows a relationship between impedance of the sensor and moisture content of the cut-off stem. The impedance changed exponentially with decrease in the moisture content. Therefore, the fabricated sensor can easily measure the target range of approximately 40% to 100%. Furthermore, we observed a stem EC value of 4.8 milligipens per centimeter and a stem temperature of 26 degrees Celsius. From this result, it was proved that the fabricated sensor can measure plants. Finally, we experimented with an actual plant. First, the fabricated sensor was inserted into this tomato and fixed with an ABS resin package made by a 3D printer. Next, the temperature, humidity, and CO2 concentration of the plant growth chamber were set constant. Only the light intensity was changed and the change in the plant and soil moisture content was measured. There are experimental setup. The experiments are also mimicked and dual variations in a plant, and the result corresponded to change in the moisture content of a plant under water stress cultivation. This figure shows the experimental result. The horizontal axis is time. The left vertical axis is plant moisture content value, and the right vertical axis is soil moisture content value. The blue line is the measured change in the plant moisture content value, and the orange line shows the soil moisture content value in the plant growth chamber. The experimental results shows that plant moisture content value change as the soil moisture content decreases. This is comparison of our study and previous study. The right figure in this result of previous study analyzed the moisture content in the tree and shrubs plant stem. As shown here, an increase in soil moisture content caused a change in a moisture content within a plant. This tendency is similar to the result of our study. It is suggested that fabricated sensor is capable of non-destructive and real-time measurement of moisture content values in plant shoots. This is the conclusion. We propose a microsensor device for minimally invasive measurement of moisture storage in plant shoots, and we have successfully realized a measurement of moisture storage sensor with moisture content sensor and RTD EC sensor. In addition, we determine the feasibility of non-destructive and real-time measurement of the moisture storage in plant shoots. And in the future study, completion of the purpose proposed sensor device by integration with the sub-flow sensor. That brings me to the end of my presentation. Thank you for attention.